Crankshaft machining is a dynamic and precise process that transforms massive raw materials, often weighing between 1 to 5 tons, into the vital heart of an engine. This machining journey involves shaping, turning, and grinding the rough metal into a balanced, high-strength crankshaft capable of withstanding immense forces. The power of spinning such colossal workpieces while cutting them into exact forms is unmatched, combining both engineering precision and raw mechanical force. Every crankshaft produced carries the thrill of motion, embodying strength, endurance, and the precision required to drive engines smoothly and reliably across industries and applications. High-strength, full-penetration welds ensure durability and leak-proof sealing. The steel extension assembly involves connecting welded pipe sections to the valve body, ensuring proper alignment, structural integrity, and accessibility. It provides extended reach for installation, operation, and maintenance, while maintaining pressure containment and protecting the valve during pipeline construction. Testing includes hydrostatic, pneumatic, and functional checks to verify valve strength, sealing integrity, and operational performance under simulated pipeline conditions. Sandblasting cleans surfaces, removing rust, scale, and contaminants effectively. Painting provides a protective coating to prevent corrosion, enhance durability, and ensure long-term performance. Specialized industrial paints are applied after surface preparation, meeting pipeline standards for adhesion, chemical resistance, and environmental protection. Crankshaft material, high-strength forged steel or special alloy, is selected to withstand immense loads, thermal stress, and continuous operation, ensuring durability, toughness, and dimensional stability throughout marine engine service. Rough machining of crankshaft journals. In this stage, the crankshaft journals are cut to remove excess material from the forged blank, forming the basic cylindrical shape. Large lathes and precision cutting tools are used to achieve uniform dimensions while maintaining structural integrity. Though tolerances are not yet final, this process establishes the foundation for later finishing. Proper rough machining ensures stability, minimizes deformation, and prepares the surface for high-accuracy finishing operations. Crankpin turning, precisely shaping crankpins to required dimensions. This process involves accurately machining the inner width between crank webs, ensuring precise spacing, parallelism, and smooth surfaces, which are critical for proper bearing fit and engine performance. Flange end face finishing, achieving flat, smooth, and precise surfaces. Strict geometric accuracy is maintained, so surfaces remain square within 0.02 mm tolerance, achieving 80% flat contact, ensuring reliable assembly, smooth rotation, and long-term durability under load. Journal finishing with a carbide tool, ensuring smooth, precise surfaces. Chip thickness at the micron level, ultrafine precision cutting achieved. Careful polishing reduces microscopic irregularities, enhances surface smoothness, minimizes friction, and improves bearing contact for optimal engine efficiency. Final precision cutting produces smooth, dimensionally accurate crankpins, ensuring proper bearing fit, reduced wear, and reliable engine operation. During ultrafine cutting, material removal is controlled at micron levels, achieving exceptional accuracy, surface quality, and consistent dimensional precision. At this stage, the crankshaft retains machining marks and rough surfaces, requiring precision finishing to achieve final dimensions, smoothness, and functional accuracy. Accurate drilling of bolt holes on the flange face ensures precise alignment, secure fastening, and reliable connection to engine components. Edges of the crankshaft are carefully chamfered to remove sharp corners, prevent stress concentration, and improve assembly safety. A custom-built tapping machine, designed and produced internally, allows precise threading of bolt holes in crankshaft flanges. Its robust structure and optimized control system ensure consistent accuracy, improved productivity, and flexibility for both new manufacturing and repair operations. The tapping process is carried out at a molten metal temperature of 460 degrees Celsius, ensuring proper fluidity with a tapping weight of 4 tons to maintain stable casting quality and productivity. The pouring operation is one of the most critical steps in the casting process, as it directly affects the internal quality, surface finish, and dimensional accuracy of the final product. In this process, molten metal is poured into the prepared mold cavity at a controlled pouring temperature of 343 degrees Celsius. Maintaining this precise temperature is essential to ensure that the metal has sufficient fluidity to completely fill the mold without causing premature solidification, which could lead to misruns or cold shuts. At the same time, excessive superheating is avoided to minimize oxidation and gas absorption. The operation is carefully timed with a pouring duration of 58 seconds, which is optimized to achieve a smooth, continuous flow of molten metal into the cavity. A steady pour rate helps prevent turbulence, which can introduce air entrapment, slag inclusions, or erosion of the mold surface. Together, controlled temperature and timing guarantee uniform solidification, reducing defects and ensuring high-quality castings. The molding operation involves creating a strong and precise mold that can withstand the high temperatures and pressures of molten metal. In this process, high-quality silica sand is mixed with a carefully measured amount of resin and hardener. The resin acts as a binder, while the hardener initiates a chemical reaction that quickly solidifies the sand, forming a rigid mold with excellent dimensional stability. This ensures the mold maintains its shape during pouring and cooling. Following molding, the coating and preparation stage is carried out. An alcohol-based coating material is applied to the mold's inner surface to improve its heat resistance, prevent metal penetration, and enhance the smoothness of the final casting surface. The final pouring operation is performed at a carefully controlled temperature of 363 degrees Celsius, ensuring optimal metal flow and complete mold filling, while minimizing defects such as shrinkage or porosity. After solidification, the casting undergoes the finishing operation, which includes removing excess material, cleaning surfaces, and performing inspections to achieve the required dimensional accuracy and surface quality. Drilling involves creating precise holes in beams using CNC or manual machines. It ensures accurate alignment for bolts and connections, maintaining structural integrity while following engineering drawings and tolerance requirements. Cut to length involves trimming beams to specified dimensions using saws or cutting machines, ensuring accuracy, consistency, and minimal material waste. Nesting optimizes beam layout to minimize waste and maximize efficiency. Cut to shape involves profiling beams into required forms through plasma, oxyfuel, or bandsaw cutting, ensuring precise contours, notches, or copes for accurate assembly and seamless structural fit-up. Grinding smooths cut edges and weld surfaces, removes burrs or irregularities, enhances safety, and ensures proper surface finish for welding or inspection. Welding permanently joins beam components using techniques such as SMAW, MIG, or submerged arc. It ensures structural strength, durability, and load-bearing capacity, requiring precise parameters, skilled workmanship, and quality control to achieve defect-free, reliable connections. Cleaning removes slag, spatter, and contaminants, ensuring smooth weld surfaces. Welding fuses beam components into strong, permanent joints using methods like SMAW or MIG. Proper heat control and technique ensure structural integrity, minimizing defects while meeting strength and quality standards. Cleaning eliminates welding slag, spatter, dust, and contaminants, ensuring smooth surfaces, improving appearance, and preparing beams for inspection, finishing, or coating applications. Ultrasonic testing, UT, is a non-destructive examination method used to assess the internal quality of welds in beams. High-frequency sound waves are transmitted into the welded area using a transducer, and the reflected signals are analyzed to detect defects such as cracks, voids, porosity, or incomplete fusion. UT provides highly accurate results without causing damage to the material, making it essential for ensuring structural safety and reliability. This process verifies weld integrity, confirms compliance with standards, and prevents potential failures in critical structural applications. On April 9, 2009, the engineering company Královopolská AS carried out a hydrostatic pressure test on a newly manufactured steam condenser. The test was performed in strict accordance with the prescribed manufacturing procedures and international standards, ensuring the unit's safety, reliability, and readiness for delivery to the customer. The condenser tested was a 2-pass unit with fixed tube sheets, designed for a total heating surface of 1,728 square meters. It was built with a hot steam inlet and an expansion shell that contains a carefully arranged system of baffles. These baffles guide the steam flow and ensure effective heat transfer during operation. The heat exchange surface of the condenser consists of 3 470 straight tubes, each measuring 23 by 1 millimeter, securely expanded into the tube sheets. Inside the shell, the condenser is also equipped with 2 dedicated sections for cooling the mixture of steam and air, further improving its efficiency. This condenser was prepared by Siemens, while manufacturing took place at Královopolská AS in Brno, Czech Republic. The equipment's dimensions emphasize the scale of the unit: a length of 8, 500 millimeters, a width of 3, 300 millimeters, and a height of 7, 700 millimeters. Such dimensions highlight the condenser's role as a critical component for large-scale industrial and energy applications. Before the pressure test, representatives of the customer conducted detailed inspections of welds and tube expansions to verify quality and compliance with specifications. The condenser was then filled with water and pressurized to the required test value. The internal and external surfaces of the apparatus were thoroughly cleaned, dried, and freed of any residual water to avoid contamination or corrosion during the procedure. These preparations were essential for ensuring accurate results and the long-term durability of the condenser. Once the prescribed parameters were confirmed, the pressure test was completed successfully, and the unit was drained. Following the test, the condenser was scheduled to receive a protective paint coating and conservation treatment in line with applicable standards. A manufacturing nameplate with the required technical data would also be affixed to the unit. To facilitate safe transport, the condenser was designed to be disassembled into sections. It would be shipped to the customer together with complete technical documentation in English, ensuring clarity and compliance with contractual obligations. All parts were to be carefully packed to prevent any damage during transport. Rolling of metal sheets is a key process in modern manufacturing, enabling the creation of cylindrical and conical components used across industries such as energy, construction, shipbuilding, and heavy machinery. Among the most trusted equipment for this process are Faccin machines, known worldwide for their precision, strength, and reliability in handling even the toughest materials. At its core, Sheet rolling involves feeding a flat metal plate through a series of powered rollers that gradually bend it into the desired shape. Faccin machines are engineered to provide both high accuracy and consistency, even when working with large and heavy plates. With advanced control systems and robust designs, these machines allow operators to achieve exact geometries while minimizing material waste. One of the standout capabilities of Faccin machines is their ability to handle plates up to 120 millimeters in thickness. This is particularly valuable in industries that rely on heavy-duty structures, where strong and thick materials are required for durability and safety. Rolling such thick sheets demands immense power and precision, both of which Faccin equipment delivers reliably. In addition to thickness, the maximum sheet width of 3,000 millimeters expands the versatility of the machine. Large width plates are commonly required for the fabrication of storage tanks, wind towers, and industrial vessels. Having the ability to process sheets of this scale reduces the need for additional welding and assembly, resulting in stronger and more efficient structures. Another important feature is the ability to achieve a minimum diameter of 400 millimeters when rolling sheets. This specification highlights the machine's flexibility, as it can produce relatively tight curves despite handling extremely large and thick plates. This capability is essential in producing cylindrical shells, cones, and similar components required in pressure vessels and piping systems. Beyond their technical specifications, Faccin machines are also recognized for their ease of use and safety. With ergonomic controls and advanced hydraulic systems, operators can manage the rolling process with greater confidence and less physical strain. Automated features further enhance productivity, ensuring consistent results across multiple runs. In today's competitive industrial environment, efficiency and precision are not optional, they are essential. Faccin rolling machines provide manufacturers with the ability to meet demanding project requirements while ensuring cost-effectiveness. By combining strength, flexibility, and technological innovation, they play a vital role in shaping the future of heavy fabrication. Rolling sheets on Faccin machines is not just a mechanical process, it is a cornerstone of modern engineering. With capabilities such as 120 mm maximum thickness, 3,000 mm maximum width, and 400 mm minimum diameter, these machines empower industries to create the large-scale, high-quality components that drive progress worldwide. Modern manufacturing demands speed, precision, and efficiency, and two technologies at the forefront of this transformation are laser cutting and automated welding. Together, they form the backbone of advanced production processes across industries such as automotive, aerospace, and machinery. Laser cutting is a highly versatile process that uses a focused laser beam to cut materials with exceptional accuracy. Unlike traditional mechanical cutting methods, laser cutting delivers clean, burr-free edges with minimal material waste. It enables manufacturers to work with complex geometries, fine details, and thin or thick materials alike. The non-contact nature of the process reduces tool wear and minimizes deformation, ensuring consistent quality even in large-scale production. From lightweight automotive components to intricate parts in electronics, laser cutting has become essential, where precision and repeatability are critical. Complementing this is automated welding, a process where robotic systems carry out welding tasks with high speed and precision. Automation ensures consistent weld quality, reduced human error, and improved safety by minimizing operator exposure to heat, fumes, and sparks. High-speed automated welding is particularly valuable in industries requiring strong, durable joints under demanding conditions, such as car frames, aircraft structures, and heavy machinery. With integrated sensors and monitoring systems, modern welding robots can adapt in real time to variations in materials or positioning, guaranteeing reliable results. When combined, laser cutting and automated welding offer manufacturers a powerful synergy. Components cut with millimeter accuracy can be joined seamlessly, enabling lightweight designs with optimal strength. This is especially vital in the automotive sector, where weight reduction directly translates into improved fuel efficiency and reduced emissions.